Welcome back, students. So we are into chapter number 3 of your textbook, and we are studying the harmonic forced vibrations harmonically forced vibration of single degree of freedom system. Okay, so degree of freedom in this case is only one, and that is x basically. Yeah, so although we have three components, so we have three components like this. So K, C, M. However, we have only one variable, that x. So xt only is the variable which is a function of t, but xt is only one degree of freedom. So this is the only degree of freedom, and hence this is single degree of freedom system. Okay, so remember, this is the single degree of freedom system. Okay, as in contrast to this 2 degree of freedom system that we will study later on, where we will have two displacements at the same time. So example of 2 degree of freedom system will be something like this. So this is M1, K1, and then you have another thing here, so K2, this is M2. So in that case you will have X1, and this is X2. In this case this will be 2 degree of freedom. Yeah. So this we will study later on, but right now we are focusing on a single degree of freedom system only. Okay. So we have the equation now, right? So as for this harmonically forced vibration of single degree of freedom system, that is this system which is being excited by F equal to F naught sine omega t. This is the force we are applying. So this will be mx double dot plus cx dot plus kx equal to F naught sine omega t. So we have already solved with one method. Yeah, and this is equivalent to saying actually this is valid even if this is x dot plus kx equal to 0, right? So, and this is what is called this is homogeneous solution. We call it homogeneous solution. And mx double dot plus cx dot plus kx equal to F naught sine omega t. This is the particular solution, or particular integral also you call. So particular solution or integral. So this means actually two equations. One, for example, if you add both of them, let us say we add this and this, both of them, then also we get the same equation, because anyway mx double dot cx dot plus kx, if that is equal to 0, so if you are adding 0 both the sides, still we get the same equation like this one. So that means any differential equation which is not homogeneous, homogeneity is automatically implied, because this is automatically a solution of non-homogeneous differential equation as well. So you have to always take care of this. Yeah. Okay. Now we solved this homogeneous solution in chapter number 2. As I say, this is chapter 2, and here particular solution we are doing now, that's a chapter number 3. Okay. Now it's possible that you can find out the solution, both the solution together. You don't need to actually have the homogeneous solution first and then have the particular solution. Okay, how can you do it? Laplace transform method automatically take care of both of them. So if you take let's do the Laplace transform method, apply that, and let's see how can we find out the solution. The solution will have both the things, homogeneous solution and particular solution combined automatically. Okay, so that we will see. Okay, so let's write the equation again. We have mx double dot plus cx dot plus kx equal to f naught sine omega t. Okay, now let's apply the Laplace transform to all of it. So what we get? Mx double dot plus cx dot plus kx equal to Laplace transform this side as well. So f naught sine omega t. Or we do the next thing as we have done earlier. So we get m, and then we will have here, so we have s square. Okay, then we have minus, and then we will have the x at 0, so s times, so we have s times x at 0 minus x dot as 0, so we have this. Then we have this one, so we have c, and then we get s, we have minus, we have x at 0, then this one, so we have k, sorry, you also have to write x s here, so we will take xs, no problem. So we will take s square x, so you have to write here s square x s. Okay, similarly here this will be s times x. Okay, where x s is nothing but Laplace transform of xt. So this is there. Okay, so we have, that's why we have to write that. So we have that, and then plus k times x s. Okay, and that will be equal to what? Of this one. So what is the Laplace transform of that? That will be f naught and sine omega t. Laplace transform, you can get it from some table or simply Wikipedia. You can get that in some standard textbook, or you know already because you had this course. So this will be simply equal to the Laplace transform of sine omega t is omega divided by s square plus omega square. So you have Laplace transform, all the equation transformed by the applying the Laplace operator, and or we will get, again we can find out from here. So we get xs, which is common, and then you get ms square, then you get cs plus k, like this. Okay, and all other thing we can also put that side. So this will be equal to, and then f naught omega divided by s square plus omega square. The rest will go that side. So plus ms x at 0 plus mx dat at 0 and plus c x at 0. Okay, so you have this. Okay, now xs will be, now we have to divide all of them. So simply we get f naught omega divided by s square plus omega square, and then you get ms square plus cs plus k, okay, plus plus this we have ms x naught x at 0 plus mx dot 0 plus cx 0 divided by, you get ms square plus cs plus k. Okay, you can recognize here this part comes from the free vibration. So in the chapter 2 we got, when we applied the Laplace transform, we got this value. Okay, so this one you get the free vibration terms you get, right? So this is free vibration, and this one you get the forced vibration term. Yeah, so this is a forced vibration term, but the complete both of them if you add, then you get the actual, the summation of the two is the net displacement. Okay, so here this is the xs you get, and of course x t, that is a displacement. If you know, you have to take L inverse of xs, okay, and then you will get two part, one by inverting this one and one by inverting this one. So one you get x force vibration, let's call it xf, or this also call it particular integral. So as you said earlier, so let's call it xp. This is also particular integral. Right here, particular integral, we call it a particle solution, right? So, and this one is homogeneous solution, right? So homogeneous solution as well. So h, so xp plus xh t, right? Where, so this one, let's call it so where x p t equal to L inverse this one f naught omega divided by s square plus omega square ms square plus cs plus k term you get, okay, and xh equal to of this one. So Laplace inverse of this term, which is msx at 0 plus mx dot at 0 plus cx0 divided by ms square plus cs plus k. So this value you get from that side. Yeah. So again, I'm not going to work out in details, but the idea was to just to demonstrate that you can apply the Laplace transform to get the complete solution. Yeah, so the forced vibration term, apart from that, you also get the free vibration term, that is, you get both homogeneous solution and the particular integral or particular solution as well included in the solution when you use the Laplace transform method. Okay, so you can try yourself. Now you can find out exactly what is the value here, and you will find the same solution that we got last lecture, right? So you will get the, inverting that, you will get the same particular integral or particular solution here. Okay, so I leave that on you to do. So let's discuss about one more convenient method. Okay, so let us say you want to solve the same equation, this mx double dot plus cx dot plus kx equal to f naught sine omega t, right? So what we are writing here, we can also write this as imaginary of f naught cos omega t plus I f naught sine omega t, or we can call it f naught and then or basically imaginary of f naught E, okay, and then I omega t. We write like that. Yeah. So we can also treat this equation as applicable to a complex number as well. Okay, so where we can use x as a complex number. So the solution, if f is complex, then solution also we get complex number, right? So basically we want to find out if the input here, force input, is f naught sine omega t, then this is real. We expect the solution also has to be real. If instead of giving this one, if let's say we want to solve this equation, mx double dot c x dot plus kx equal to f naught e I omega t, okay, then whatever solution we get there, from there you can find out based on whether our force is real, the real part of that force, the corresponding real part of x will correspond to each other, right? So for example, in this case, this imaginary part of this is our force applied. Hence whatever answer we get, answer will be imaginary part of whatever x we get from this equation, right? If our force, if force is equal to f naught sine omega t, which is imaginary part of this. Yeah. So this property we can use basically, and that makes it quite convenient. You can very conveniently you can find out something, and also you can understand then the vector representation of the forces. Vector method, if you want to work with vector method, you can just apply onto it. And also it gives you more insight basically, and also this makes it life simpler. Okay, it becomes very easy to do, and it has a different meaning as well. Okay, so let's understand what is the meaning of it. So we rewrite the equation. Okay, rewrite the equation. So we write mx double dot plus cx dot plus kx equal to f naught e I omega t, and we want to have a solution for this one. If we have this solution, we can figure out if here instead of f naught sine omega t, if you have f naught cos omega t, then what will be the solution? We can also find out. And instead of this, if you have f naught sine omega t, then what will be the solution? That we can find out. So basically general purpose we are going to find out from there. I think this is a vector notation. This vector notation is complex notation, that it also gives us some meaning. Okay, so before we understand that, let's solve this one. Okay, so if that is the case, solution as such, as in fact we have seen already, solution has sine, if it is sine omega t, it has, solution x has sine omega t minus phi. Some phase difference is there. Similarly, you can try here, if you have f naught cos omega t, you will get the solution f naught cos omega t minus phi there also. So there is a phase difference you will observe. So to begin with, we can guess, right? So we guess the solution will be of this form, x equal to x naught e I omega t minus phi. Okay, this is our solution. Okay, only thing is, now we have to find out, find x naught equal to what and phi equal to what. That's we want to find out. Okay, and that's what we did yesterday. The whole lecture was on finding out x naught and phi only. Okay, so here also we are doing the same thing but in different way. Okay, so this we are going to plug in here. So what do we get? Okay, first we have to find out if x is like this one, so x dot will be equal to x naught, then I omega, then we have E I omega t minus phi. Okay, x double dot will be equal to, we get minus x naught omega square, then E I omega t minus phi. Okay, so we got that. Now we are going to plug in x double dot here, and what we get, m times minus x naught omega square. Okay, and this term appears in all of them, so let's make it common. So I will just rewrite this way. So, and x naught is appearing everywhere, so x naught E I omega t minus phi will be common, right? Common to all of them. Yeah. So we have m times x double dot, and x double dot is x naught and E I omega t minus phi, and then you have omega square just, so m omega square and minus sign, so we get minus m omega square here. What about this one, cx dot? Okay, cx dot, what we get here, x naught I, here x naught e to the power I omega t minus phi, we already have. What we did not count yet was I omega, and from c, from here we get plus I c omega. Yeah. From the last one, k is, everything is from here is already there, so what we have is k, right? And that is equal to, what we get here, f naught E I omega t. So we got the equation here, or we call it or. So compare from here to here. Okay, so we can get rid of E I omega t from both the sides. So what we get, x naught e to the power minus I phi. Okay, and then we get k minus m omega square plus I c omega equal to f naught. So I omega t gone from both the sides, and what do you get? We get now or x naught e minus I phi is equal to f naught divided by k minus m omega square plus I c omega. Yeah, okay. Now, if you have to find out x naught, what would you do? X naught, if you have to find out, then we take the magnitude on both the sides, right? So magnitude meaning that we have to do x naught, we apply this operator, we find out the magnitude of this complex number, so we get like this, f naught divided by k minus m omega square plus I c omega, right? That's what we find out. Yeah. Okay. So let's see. Okay. From here, x naught is a constant number for us, e to the power minus I omega t. The magnitude of e to the power I, e to the minus I phi is sin square phi plus cos square phi, root under of that. So sin square phi plus cos square phi is 1. So what we get is x naught only. So magnitude here x naught. X naught is itself a magnitude. Okay, so x naught is a positive number. Yeah. Okay. Now equal to f naught divided by this. So what do you get from here? We get f naught divided by and this one, the magnitude of that. The magnitude of this is what? Root under and k minus m omega square of that plus c square omega square. This is what we got yesterday, but we took long time to derive it. We got immediately. Right? Okay, so once we have x naught, the next thing is to find out the phi. Okay, so how will you find out the phi given this equation? Now x0 we know already, so we can find out e to the power minus I phi. We can find out now because we know the x0 now. So x0 will be this divided by that. So what do we get? We get this value and we'll divide by that value. So we get 1, we just write this one first. So if not, then k minus m omega square plus I c omega, okay, multiplied by, since we have to divide by this one, so we multiply, so we write this first, okay, so k minus m omega square plus c square omega square divided by f naught. So what we get? Okay, or e minus I phi will be equal to, which is equal to, actually this is equal to cos phi minus I sin phi, okay, is equal to this value. So f naught cancels out, and what do we get? We get this, so we get this one, k minus m omega square plus c square omega square divided by this value, so k minus m omega square plus I c omega. Okay, next we can, since here in numerator you have I appearing, so here in the denominator we have, so we can accordingly bring it up, and what do we get? We get like this, equal to we multiplied by k minus m omega square minus I c omega, okay, and what do you get? We get k minus m omega square minus I c omega divided by, okay, so if you multiply this one with this, what do we get? We get k minus m omega square of that plus c square omega square, but here we already have the square root of the same number, so what we get finally will be root here, will be k minus m omega square plus c square omega square. So that's what you get, cos phi equal to, that really means if you equate the real part and the imaginary part, so automatically we get sin phi equal to c omega divided by this, and cos phi will be this divided by this. So we have minus sign here, so simply we get tan phi is equal to, we get c omega divided by k minus m omega square. The same thing we got yesterday, exactly the same value. Okay, so what we see here is basically we get the same, everything same, and only thing is we treat it like this as a complex number, that is all. Now just to relate that we had mx double dot plus cx dot plus kx equal to f naught sin omega t here, there. So from here to how to find out the solution when you had sin omega t there. So sin omega t is the imaginary part of that, right? So if you had actually imaginary part of this one, solution will also be the imaginary part of that. So solution imaginary part of x is actually x naught sin omega t minus phi, right? So solution will be, if f equal to f naught sin omega t, solution will be x naught sin omega t minus phi, where x naught is given by this one and phi is given by this one. So you get from there. Okay, if force is f naught cos omega t, then actually the force is the real part of F naught EI omega t. Hence the solution will be real part of the x. We assume the solution will be x equal to x naught cos omega t minus phi, and hence what you see here is the whatever, if you sign here, same thing in x also will be sign, however there will be a phase difference there. So that is. Now this complex notation also gives some insight basically, yeah, and give some idea how can we solve it graphically, or how we can represent graphically basically, yeah. So F is equal to F naught EI omega t, okay, so which is equal to F naught cos omega t plus I sin omega t. If we want to represent this in a complex plane, how will we do that? We will be like doing like this, right? So this will be C, this will be real, this is imaginary, right? And if you have F here like this one, right? This is F, where from here to here we have F naught, and then you have omega t here. So this is how you will represent F, right? So, okay, so F naught cos omega t. So this is from here to here F naught cos omega t, and from here to here you have F naught sin omega t. So this is the complex representation of F, yeah, okay. Now if F is like this one, let's see the other components, how they look like, okay. So remember that our equation mx double dot plus cx dot plus kx equal to F here, F, which is F in this case is F naught EI omega t. Here basically this is the balance of force basically, right? So this is a balance of force, So individual, that means this is also a force, this is a force, this is also a force, and this is also force. So individually the components of forces, how they actually are in equilibrium. So graphically we can represent that, okay. So how can we do that? We know that if the force is F naught I omega t, we know that x is x naught E I omega t minus phi, where x naught and phi we know already, just now we worked out, and yesterday we got that, okay. So is like this one, and from here we can also find out if x dot will be equal to nothing but x naught will be equal to x naught I omega EI omega t minus phi, and x double dot will be equal to minus x naught omega square EI omega t minus phi, okay. So the force mx double dot, first force, that becomes minus m omega square x naught, right, EI omega t minus phi, right? Okay. Similarly, cx dot we get equal to so c times this one, so we get I c omega x naught e to the power my I omega t minus phi. You got that? Okay. Next, kx equal to k times this, so we get k times x naught ei omega t minus phi. So all are forces only, right? So we have representation for this force, the applied force, as this one. If you want to represent this similarly, we can also do that, right? And how will we do that? So see here. First we have to see how if omega t is like this one, and we know the phi, so if x is like this, so individually also we can do first. Okay, so let's do for mx double dot. How will it look like? It will look like this one, something like this. How? This is if omega t minus 5. So let us say this is omega t, and this is phi. So this is from here to here omega t, and from here to here phi. So this value is omega t minus phi. Okay. But what it says, minus sign here, that is this is not this side, but this is the opposite side. So this is, if you extend this line, so if you extend it further like this one, so mx dot double dot is something like here. So this is mx double dot, which is minus m omega square x naught, right? So this is how the representation of this will be, ei omega t minus phi. This is how it will look like, and which is representation for the inertial force here, right? So this is what we get for this one. Yeah. Okay. Now next thing is cx dot. I will find out. So we have the same configuration here. So it's imaginary. Here it is real. This is imaginary. And then what do we have? Similarly, we have to work out the phi first. So this is the phi, and then this one is omega t, and then from here to here is phi. Hence this one will be omega t minus phi. Yeah. So, but what we see, from here to here, we can say that from here to here, what is the direction? Direction is e to the power I omega t minus phi. But there is I multiplied here. So the moment you multiply by I, that really means if this is represented by this vector, you multiplied by I, that you have rotated by 90 degrees from there, right? That's how it looks like. Yeah. So that's what the complex algebra says. If you multiplied by a complex number by I, you are rotating that vector by 90 degrees, right? So that's what or you can actually spell it out. You can say here cos omega t minus phi plus I sine omega t minus phi, then multiplied by I. Then what you get? You get sine omega t, not sine, you get minus sine omega t minus phi plus I cos omega t minus phi. So that is actually the 90 degree of that. So you get the direction will be like this. So from 90 degree, you get like this. Yeah. So from wherever your representation will be 90% degree from here. So with respect to 0, you are drawing like this. You go like this one. Yeah. So it is 90 degree from this line, and this one is I here. This is I c omega x naught e I omega t minus phi. That's what we get from there. Okay, now we have the this we found out. So m x dot represented like this one, cx dot represented like this one, and then kx we can find out from here. So real, imaginary, and then this one is omega t from here. So from here to here we have phi, and from here to here we get omega t minus phi, and the kx is kx naught e to the power I omega t minus phi. So omega t minus phi, so omega t minus phi is this one. So along this line will be, so this will be something like this one. Yeah, and what is this one? This is kx naught e to the power I omega t minus phi. So what do we have? Now summing them, we have to sum them up. Okay. So how will it look like? Okay, this will look like this. So let's draw it here. We are going to draw it here. So like this. Okay, so force, let us say force is like this. Okay, this is our force. Okay, now we have from here to here, we know that this is omega t, this is imaginary, sorry, this is real axis, and this is imaginary axis, and this is omega t. Now kx term is phi from here, so we have, maybe we have something like this. So from here to here is phi, so that here to here we have omega t minus phi. So we may have the kx term. So this is f term, this is kx term, it's like this. Then we have cx dot term. So kx term is this one, kx naught e I omega t minus phi. This is the kx term. Then we have this one, cx dot term, which is perpendicular to kx, right? So we can draw like this. We go like this. Yeah. So this one is 90 degree, and from here we go like this one. So this is cx dot term. Yeah. Then we have mx double dot term, which is opposite to kx. So this is parallel to kx because this is on the same line. Yeah, but the opposite direction. So same line as this one, but opposite direction. Means parallel to this one, but opposite direction. So this is how it will be like this. Yeah, and this is mx double dot term. Yeah. So this is how the vector notation we can use to actually see how the forces are balancing, and also you see the phase, basically what the meaning is the phase. So if f is omega t, for kx, force produced in the spring will have f phase omega t minus phi. Okay, so difference of phi, then cx dot will have 90 degree rotated from there. Yeah, so phase will be omega t minus phi plus pi over 2. That's really means, right? So actually angle is here omega t minus phi plus pi over 2, then you get cx dot. The phase angle for that will be omega t minus phi plus pi over 2. And mx double dot it will have the difference from here. So 90 degree from here to here, and then further 90 degree from here. Okay, so you get 180 degree from here. Yeah, so phase difference between this and this will be 180 degree, and hence you have like this. And this is F has to be summation of all of this, because we have summation of this. So this is something like a vector summation you get, and you get all the three components added together, you get equal to F. Now let's compare three conditions. Okay, so condition 1, omega less than equal to omega n. Condition 2, omega equal to omega n. And condition 3, omega greater than omega n. Okay, and this is the letter representation we have already. So what happens in all the three cases? Let's compare. Now we know that mx double dot is equal to minus m omega minus m omega square, and then we have x naught, and we have e I omega t minus phi, right? And then we have cx dot equal to I c omega x naught e I omega t minus phi, and kx equal to k then x naught and e to the power I omega t minus phi. Okay, now when let's start with the condition number 2, condition 2 first. Omega equal to omega n. We know that omega n is equal to root k over m. Right? This is from here, what do we if you compare this and this? Okay, so that really means omega n square equal to k over m. If that is the condition, second condition is omega equal to omega n square. So let us see if you compare a mx dot and kx. So just magnitude if you see, okay, in what condition mx double dot and kx will have same magnitude. So the magnitude here is condition equal to what? For mx double dot is equal to kx. Okay, same magnitude. If it's what condition we get. Okay, so what we will see here is m omega square has to be equal to that condition is m omega square equal to k, or omega square equal to k over m equal to omega n square. So basically what I mean to say is when omega is equal to omega n, then mx double dot becomes kx, okay, magnitude wise. So when omega equal to omega n, then mx double dot becomes equal to kx. That really means what? That really means this one kx and mx double dot length becomes the same in that case, right? So how will look like that? In that case, this will simply look like this. So you will have from here to here, then from here to here you will have like this, and then we have same length going like this one, and then we will have like this. Yeah. So if omega t is like this one, so that this will be kx, this will be mx double dot, this will be cx dot, and this will be f. So this is how the relation will be in that case. So how they are related. In that case, if omega equal to omega n, this and this will be parallel and opposite and equal. So what you see here is a rectangle basically. So this will be a rectangle. If that is the case, you know that this is pi over 2. Hence, this also will be pi over 2. Right? So, but this from here to here, we call it phi. So, this is phi equal to pi over 2. So, phi equal to pi over 2 when omega equal to omega n. Okay. Okay. Yeah. In this case, what you see in this case is phi is less than pi over 2, but in this case the phi is exactly equal to pi over 2. Now let's see how depending on the omega how this value varies. So what you see, k has magnitude wise it has no dependence on omega, so magnitude of k will be the same always. C x dot has one omega term here, just c times omega. So as omega increases, this value will also increase. So more omega means more this length, and then you have mx double dot equal to you term omega square term. Now omega square term means this varies much faster than c. Okay, so what you see here, if you change omega, k value, the length remains the same. If you increase omega, cx dot will increase a bit. However, mx double dot will increase much more compared to c omega, compared to cx dot. Okay, so that really means if mx double dot is this length when omega is low, say omega equal to omega n, you increase it to omega equal to omega n, then mx double dot will be comparable, will be equal to the length of kx, and when you have omega greater than omega n, then the length of mx double dot will be greater than kx. Okay, so how did it look like? This is the first case already. Okay, mx double dot, because of if omega is lower, then because of omega square term, mx double dot will be smaller than kx. Okay, then if omega equal to omega n, this and this becomes equal, then omega greater than omega n, then mx double dot becomes larger than this one. So the third case, this is second case, this is the first case, and the third case will look like something like this. So here, okay, and then kx remains the same like this. Okay, and then you have cx dot, and then parallel to this parallel to that, but much bigger than this will be mx double dot. So this is mx double dot, and then you have f like this one. So this is f, this is kx, cx dot, and this one angle between here to here is nothing but phi. Now what you get here, phi will be more than pi over 2. Here phi equal to pi over 2, and in this case phi will be less than pi over 2. So this is the comparison. So maximum how much it can get, you keep on increasing this one, increasing this one, and then you will get maximum phi, right? So you can keep on increasing, finally this will be as if this line is the extension of this line, so phi maximum will be pi, okay, 180 degree. Okay, so maximum, that's why phi varies from 0. Okay, so when omega is very, very small, you get 0, and from 0, why 0? Because if omega is very small, Cx dot will be 0, mx double dot will be also 0, because this depends on omega. This depends on omega square. So this will be a small, this will be also a small. Hence, you have the f, and f will be balanced by kx only, not because of this. And hence, you have phi equal to 0. And then if you increase it, you will be something like this, increase more, then phi becomes equal to pi over 2, even more, and then it becomes more than pi over 2. And at the end, if omega is very large, then you get phi equal to 180 degree. Okay, that is all.